Good evening. Today we are here to discuss this chapter called Solutions. Now this comes under Physical Chemistry of your 12th standard syllabus, and it happens to be a really fascinating chapter. If you look at this chapter from an examination point of view, then probably this chapter looks like a standalone chapter, but it does have some intersections with various other chapters. As in, I'm trying to tell you that it is connected to different chapters, many other chapters. For instance, basically if you look at the name of the chapter, it is solutions. So what is a solution? How do we define a solution? In that, you can actually go into the details of solute, solvent, different types of solutions, and so on and so forth. But we've been always taught like dissolves like, as in water is actually a polar molecule. It's a polar substance in the liquid phase at least, and if you put polar substances, then it is likely that water actually dissolves that substance. So water is actually covalent, but it is also polar, but it happens to dissolve ionic solids like NaCl, alkali metal chlorides and stuff. Maybe not all of them, but definitely quite a bit of them. And it dissolves ionic solids. It dissolves sometimes molecular solids like sugar, for instance. So if you look at the sugar molecule, it is actually covalent, and it does have some bits and pieces of polar pockets, so to speak. So how does water manage to dissolve so many different substances? Yes, and is benzene soluble in water, and so on and so forth. So these things, the very basics of this chapter can be very fascinating. Having said that, maybe the basics are not often tested enough. The numerical part, the core chemistry part of this particular chapter is supremely scoring, and that is where actually you get a lot of brownie points. That is where you actually have immense scope for doing really well in terms of your examinations. But what happens when something dissolves in a solvent? That question itself is so fascinating. It has such immense possibilities that you can literally get lost in it for years. There are so many different kinds of solutions, the different methods or different aspects or reasons as to why how a covalent solid like sugar is soluble in water, how NaCl is also soluble in water, NaCl being an ionic solid. So these different types of contradictions. Now this is just we are just scratching at the surface of the tip of the iceberg, so to speak, because like dissolves like is easy in terms of non-polar substances, but how is toluene soluble in benzene, or vice versa, benzene soluble in toluene? And how does that happen? That dynamics actually becomes supremely interesting if you want to go into that kind of a thing. So but that is not extremely relevant in terms of what you get tested in the examination. But if you look at this chapter, it's very simple. It's actually a standalone chapter, in that although I said that it has a lot of tangents, a lot of intersections with different chapters like energetics, like solid state. For instance, just now I mentioned how NaCl is soluble in water. So what happens when you put NaCl into water? So basically you have an NaCl crystal. It has a crystal lattice structure, and the solvent molecules will have to wriggle and find their way into the spaces between these ions in the lattice, and then the solvent molecules form a solvent cage. And it's very interesting how the dipoles of water are arranged in one way around Na plus, and just the opposite way in Cl minus. So that is also something which is very important. Once again, you can actually go into the differences between mixtures, the different kinds of mixtures, pure substances, mixtures. We look at mixtures. What are the different types? There are a number of types. You have homogeneous mixtures, you have heterogeneous mixtures. So where do we find solution? And then at a later stage in 12th standard, you would study something called surface chemistry, where you encounter the term colloids. So where does all these things fit in? So it's like a big jigsaw puzzle, and solutions it's actually a moderately major piece of that puzzle. And different chapters and different ideas actually come together, they converge, they confluence, it's a confluence of ideas, and then all these pieces, they fall in the right place, and then you have this puzzle solved. So that is how actually the whole of chemistry unfolds at at the senior secondary level. Having said that, this is still standalone, although it has a lot of ideas connected with other chapters. Standalone in terms of how you manage to score or approach the problems, the crux of this particular chapter. So if you look at the meat and potatoes of this chapter, let us come to it. We'll come face to face with that in a bit, but it happens to be definitely colligative properties. Let's not go there right now. But having said that, since a lot of focus is on colligative properties, so that is where a lot of questions and scoring opportunities come from, which is why this chapter is standalone. So although it has a lot of disconnected ideas, a lot of intersections with other chapters, because of the nature of the way you are tested, this becomes a standalone chapter as well. So in that way, in that aspect, in terms of how you approach to score marks in this chapter, it becomes a very standalone chapter. It doesn't have that many intersections with other chapters. So that is actually a bit of a contradiction. Now how do you approach this chapter? You start with the basics. So all these different definitions, if you look at the chapter, it has any number of definitions all the way back to maybe class 6 or 7. That is where you start with the elements and pure substances. From there until class 12, it spans across a wide body of knowledge. All these things are explored at a very good detail in class 12. So get your definitions like moles, molarity, normality, millimoles, equivalent weight, all these things, be familiar with these things, things which come from mole concept or volumetric analysis, because once again we are dealing with solutions. So obviously you are going to add an acid to a base or a base to an acid in water, and you have some salt. So definitely those things, because of the nature of the medium in which it happens, the whole chapter unfolds. The landscape is pretty much water or aqueous solutions. So since that is a given, then it only makes sense that we be thorough with these very fundamental chapters, fundamental concepts, if you will, like mole concept, molarity, normality, etc., so on and so forth. So you take NaCl. It's a crystal lattice made of Na plus, Cl minus. Na plus is surrounded by Cl minus ions. Chloride ions are surrounded by sodium ions. This is the lattice. You have lattice cell or unit cell and all and so on and so forth. So what is actually keeping this lattice together? That is what that is where we come from in terms of solid state. So the attraction between the ions, that is actually keeping this lattice together. And we have a lattice. You break it so that all the ions are in the gaseous phase and they are quite far away from each other. So each ion is very far away from every other ion. So to be able to get to that, what is required? What is that phenomenon, or what is the technical term called? In other words, what is lattice energy? Okay, so when you talk about lattice energy, definitely the Born-Haber cycle comes into play. You have an atom, you have sodium atom, you take away one electron, it becomes Na plus. Now is the Na plus ion aqueous or is it actually in the gaseous phase? So if it is gaseous phase, you dissolve it in water. When you dissolve Na plus ion in water, what happens? And why do I use the word dissolve or solve? So the very basic definitions of why a substance actually dissolves in a solution, in a solvent, comes into picture. That is actually very fair game, but you generally tend not to be tested here. But some of the really tricky ones, the tricky questions, could actually probe on these fundamentals. So something as simple as physical change, chemical change, to solvation, hydration, that is how the initial part of the chapter actually unfolds. So probably get your definitions right. It's a highly scoring chapter, standalone chapter. Be thorough with the basics and try not to have any doubts festering as far as these simple terms are concerned. Okay, and we maybe we take a stop with this Born-Haber cycle, and from this we actually proceed to the actual the real concepts of this chapter. So when I say solutions, types of solutions, so I just mentioned that like dissolves like, and I just went into how polar solvents, they are able to dissolve a particular kind of solutes, and you have substances like benzene and toluene, and when they dissolve in each other or into each other or vice versa, so you get ideal solutions and non-ideal solutions, non-ideal solutions being the latter. So how does that happen? So what is the difference between an ideal solution and a non-ideal solution? Also, the energetics. So when I say energetics, I'm talking about thermodynamics. Chemical thermodynamics is the name of the chapter. It came in class 11. So the fundamental ideas like enthalpy change. So basically you have a solute, you put it into solvent, it dissolves. Or even if it doesn't dissolve, sometimes what we do is we take something and we actually stir it or give it some form of impedance. Maybe we increase the temperature or do something. So we do something to initiate the process. Some things will dissolve quite spontaneously while others don't. Why? So that is a very important question. So the energetics of the whole process of why solutions get formed, that itself is very fascinating, very, very important. So that obviously naturally proceeds into Raoult's law of ideal and non-ideal solutions as well. So del H mix, del V mix, and expressions for pressure, partial vapor pressure in terms of solute and solvent, and the different graphs. As far as non-ideal solutions are concerned, water, ethanol, or acetone ethanol is a is an example. So that actually would show positive deviation. As far as non-ideal solutions are concerned, what happens in terms of negative deviation in terms of Raoult's law. Okay, the different graphs, those are very, very important. So I mean, I think at least in terms of NEET and JEE mains, enough questions have been already asked based on the graphs, but it would be very, very important for you to not spend a lot of time on very easy questions. Topics like these which are very super scoring, that is where you should actually, especially if it is a graph based question and not a numerical, and it comes in physical chemistry, it's almost like inorganic. Basically you either know it or you don't. That is not the time to sit down and derive the whole thing from first principles and then finally arrive at the answer. This approach is actually very detrimental. It is very counterproductive as far as competitive examinations are concerned. So that is not the way to go. So pretty much Raoult's law and ideal and non-ideal solutions, all these parameters which I had just outlined, del H mix, del V mix, and expressions for pressures in both cases with their graphs, you have to be really thorough, and definitely you have to learn by rote the examples. Some examples may not always be obvious. CHCl3 and CCl4, what kind of a solution is that? Why? So it may not always be obvious. Not every time it's an obvious thing. You can definitely deduce and find out using your logical reasoning, but maybe it's I think for the people who really want to do supremely well in exams, for them I would suggest that you actually know things inside out. All these types of solutions, it's there in many books. Go through them, remember them, and try not to forget it once you've learned it. So things like in the solid state video that we did, I said there are 14 types of Bravais lattice. Okay, so based on those unit cells, types of unit cells and types of Bravais lattice, questions have been asked, but those questions should not take time to solve in a competitive scenario. That's the point I'm trying so hard to make. Okay, and then obviously the graphs, I just outlined the importance of graphs for all these things, and please do figure out the nature of azeotropic mixtures, and boiling point composition curves for both deviations as well. Those are also supremely important. And of course, obviously, if you are given a numerical, then you should definitely know the different types of numericals that you can come face to face in an examination, and also you should know the quickest approach to be able to solve that in a quick single attempt kind of ideal case scenario. Ideally you shouldn't actually take multiple stabs at the same thing, since it's one of those simpler topics. It's not as tough or as as scheming as maybe ionic or ionic equilibrium, or even electrochemistry for that matter. So usually you have problems which are straightforward. It's usually smooth sailing. Next up, the meat and potatoes of this particular chapter called colligative properties. What are colligative properties? The definitions, the drill. So solubility curves, they are very important. And of course, what are the 4 different colligative properties, what they are, once again that becomes important. Lowering of vapor pressure, rate of evaporation, that formula, rate of evaporation, is inversely proportional to square root of density. And the modified form of Raoult's law statement, graphs, the modified form, its derivation. Okay, so basically you have no P naught minus PS, the whole thing divided by PS equals small n divided by capital N. That would be equal to WA MB by MAWB, that kind of a, you know the drill. Okay, you know what I'm talking about. So measuring, what are the methods to measure relative lowering of vapor pressure? So Oswald's method, Walker method. Not many questions have actually been asked, into the details of these methods. Maybe there have been a few numericals here and there, but it's very important that in such a scoring chapter we shouldn't leave anything untouched. Next we should move on to elevation and boiling point. So ebullioscopy, similarly the just opposite, depression and freezing point, antifreeze solutions, how they work, why they work, what do people in cold countries do, if there is ice around, why do they actually throw around some NaCl or rock salt to accelerate the melting process. So these things are related to this chapter, and that's also very important. So if you look at the qualitative properties of the four things, maybe the first and the fourth one are pretty important. The other two are very similar to each other, as in elevation and boiling point, depression and freezing point. I wouldn't say they are not important, but definitely they are not as tricky as maybe Raoult's law. Raoult's law is where you get a lot of numericals. Of late, osmosis and osmotic pressure, that isotonic solutions especially, that is the area where you've been getting some questions, at least for JEE mains level questions. So osmosis, osmotic pressure, that is the fourth qualitative property. Difference between osmosis and diffusion, once again this is just pure theory. So in osmosis, what happens basically, and what would be reverse osmosis? That comes quite late into the chapter. Maybe I'll take it up a little bit later. But osmosis, difference between osmosis and diffusion, and reverse osmosis. So that is also actually something that we need to really go and explore in great detail. Also, why do we need a semi-permeable membrane? What does it do? And you have this membrane, you have one concentration inside, you have another concentration inside. What is the definition of permeability, and why it should be semi-permeable? In which way traffic moves? Is it such that the solute particles are able to move through it, or is it just the solvent molecules that move through it? And finally, is there an equilibrium? What happens in that equilibrium? So, and when we approach that equilibrium, all these factors are very, very important. Next up, it's going to be Van Hoff theory of dilute solutions. There are 2 or 3 laws here, sub laws actually, something like Boyle-Van Hoff law and Gay-Lussac-Van Hoff law, and the third law about isotonic and isoosmotic solutions. So all these three, they come under this broad banner of blanket topic of Van Hoff theory of dilute solutions. So once again, I mean, if you look at deviations or abnormal qualitative properties, there have been some numericals there, but apart from the numericals, not much have been actually asked in terms of the theoretical aspects of these. So basically, I think it wouldn't be unfair to say that if you know the theory, you may not always be able to solve the problems, but the reverse is actually true. I mean, if you know the problems inside out, if you know what's exactly happening and how to deal with a particular kind of problem, then you can probably pretty much decipher and deduce the answer to a theoretical question in the topic. So I would say that although theory is important, so your exposure and your approach to solving a problem in the shortest possible time, and probably even effort in terms of keeping your your approach fresh through the entire duration of exams, that is also something very, very important. Yeah, once again, I just said reverse osmosis and its applications, and determination of abnormal molecular masses, so Van Hoff factor I, and what happens, what is the actual molecular mass of, say, acetic acid in a particular solvent, what happens, why. So those things are very, very important. So with that, I'm just going to wrap up this theory, this take on this chapter called solutions. So let me just quickly check if you guys have some questions. So is the amount of solute needed to form a solution is less than a solvent? this question depends on the level, actually it depends on the type of solution as well. So there are places where the strict definition of what is a solute, what is a solvent is no longer relevant, you know, when they are completely miscible. And what would you say if something is 51% and something is 49%? I mean, it's not practical to call something a solute and the other as solvent. You could call either of these as any other things, but for all practical purposes, actually we say that, you know, solute is usually found in lesser amount or concentration, whereas the solvent is usually in excess. And we also sometimes go on to generalize that, you know, solvent has its phase or its state. I would rather use the word phase. Okay, so solvent, it has its phase, and you put solute into it, and the final solution that you get, usually it has the same phase as that of the solvent. Yeah, so basically sugar or salt, we put into water, it dissolves, and the final sugar solution or salt solution, it has the same state as that of the solvent, which is water. So that is something that, you know, I think it's very basic. Yeah, so is it necessary for every solution? Maybe not. Once again, depending on levels, depending on, you know, the definition. Definition of an atom at 8th standard is not the same as the definition of an atom at class 12. So it depends on your context, but yes, usually solute is less in quantity. That's that. So sir, does the solution boil? It depends if it is a closed system. Boiling, if you define what is boiling or when it does happen, so you have a system, it's open, and it actually reaches a scenario where the external pressure and the pressure that builds up, it becomes, you know, it becomes equal. When the external pressure, when the vapor pressure equals the external pressure, that is when boiling happens. And, you know, boiling happens through the entire bulk of the liquid, so you will be able to see the bubbles coming through from pretty much everywhere in the body of the liquid. So that's that. So what are the factors? I mean, there are plenty of things. So it depends on the solute. Once again, I just told you, you know, elevation in boiling point, depression in freezing point, the whole thing actually. So what is the nature of solute? How during dissolving, or maybe even, you know, when you put a solute into a solvent, the solvent molecules, they have some interaction between themselves. The solute particles, they will have, so if Na plus and Cl minus is in a lattice, obviously these ions are interacting and they are coming close to each other because of the electrostatic force. The lattice energy is actually holding them together. Yes, that is the blanket term that we use for the electrostatic thing. The attraction is what in a roundabout manner is referred to as lattice energy. I'm not being very strict with the definitions here, but yeah, you get the idea. So when you put that in water, what happens to the dipoles in H2O, and how the solvent KH of Na plus is different from the solvent KH of Cl minus, and how do we actually get a homogeneous solution? So this whole process is, you know, it depends on solute solvent solvent interactions. Once again, it's about, you know, the energetics of the solution. So that actually takes over, and how or what we put into the solution, the nature of the solute particles, and pretty much the entire, you know, gamut of interactions of all these things in the system, that actually determines how the whole thing happens. Is PV equals nRT applicable for a solution? That is another question. So pressure into volume. So what is pressure? What is the value of P there? What does it refer to? So PV equals nRT is pretty much a gas inside a closed system, and that too only for ideal gases. So at, you know, very low temperatures and very high pressures, PV equals nRT doesn't hold, and this is strictly for gases. But yes, I mean, if you have a liquid in a closed system, so that is going to give you some vapor pressure, so there is going to be some vapor inside, and that vapor is actually gas molecules, right? So it depends. Once again, is it applicable for a solution? In some cases, yes. Well, I think with that we can actually wrap up this section, because I'm getting the question from the same person. So is it necessary for every solution to exist in liquid state? Not necessarily. Solid solutions are there again. Once again, alloys. So stainless steel is again a solution actually. So it's homogeneous. It's a homogeneous mixture. It's a solution. Amalgam, once again. So mercury, sodium, mercury amalgam or any amalgam for that matter. So I think with that, let us wrap up this section on solutions. I definitely had fun. I hope you had fun too. Thank you.